chemical kinetics. We're taking chemical kinetics first, and we're going to follow it up with equilibrium. Equilibrium makes a whole lot more sense if we get a firm grasp of chemical kinetics first. So what is chemical kinetics? Kinetics is like a physics term. It means motion. Something's moving to be kinetic. So we're studying reaction rates. How fast is something happening? And the general expression for reaction rate is you measure the concentration of some component in the reaction, and it can be anything. We could say A plus B yields C plus D. If you focus on, once that's a balanced equation, then we can focus on one or both of those. Right. Well, let's say it's some type of decomposition. Right. So B plus C. Let's do that one. A is decomposing into C and B and C. Then we can say, what's the concentration of A, final concentration of A, right? And they write it out there, but I like to use that as a representation of A at time T2, and then the concentration of A at time T1. So it's final minus initial, okay, as always. And then the time interval is T2 minus T1. How long did it take? Right. So we condense that into a delta. Change in the concentration of A with a change in the time interval. That's the generic expression for the rate of a reaction. Usually, and when we use square brackets, we generally mean the R word, molarity.
The 100 one. The molarity is thirsty.
Yeah, this is thirsty one. Volume. Yeah, let's get
I
our.
don't get the reference. Sorry. R is really thirsty. Liters.
Now, technically, you can consider A here, or we could measure the production of B or C and put those in here. And it would still be an expression of the rate of the reaction. We generally, though, we want to look at the reaction. Well, we can do two things. We can watch the reaction proceed, and that's coming up in the next slide. Measure concentrations over time. Or we can talk about the reaction in terms of initial reaction rates. And under those conditions, you don't have any B and C. You just have the A, and you watch it at the very beginning. Because what happens is, as you build up B and C, you start to get reverse reaction. So if we do initial rates, that gives us a better idea of what's actually happening with the reactants. Okay, so the next one is a data set for the reaction. Let's see, let me go ahead and erase this. For the reaction of 2NO2 is decomposing into NO and O2. They're all gases. A lot of these examples are going to be gases. It's easier to study gases, the reaction rates, than it is the others. Although it is done, but it's just when you first get started, we need the easy route. Okay, notice that at time 0, we have some NO2, 0.01 molar. And we don't have any nitrogen monoxide. We have no oxygen. That's the initial concentration. And it's often written like this, with a 0 down here. That's the initial concentration. And then as the reaction proceeds, in the first 50 seconds, you lose some of the NO2 and you produce some NO and O2. And the ratio that you produce, if the first one is 0.010 molar of this compound, and then we're down to 0079, if we subtract those two, we find out how much of this is missing. Right? How much of that is missing is 1, 2, 0, right? 0, 0. And yeah, that's right. So that's how much of this is missing. Where did it go? Well, 1 to 1, you should have 0.0021 of this show up. And there it is, 0.0021. But the ratio of this one to this one is 2 to 1. So half of that value should be over here. So this is going to be 0.0021, and this is going to be 0.0011. Rounded off. So as the reaction proceeds, we see the stoichiometry is obeyed. And if you plot the data, which is on the next slide, if you plot the data, and that's kind of hard to see, but you notice that at the very beginning, time 0 is right here. At the very beginning, you have all of this nitrogen dioxide up here, and you have no products down here. And as we proceed, we find that the NO2 decreases and the NO and the O2 increase. But if we look at the reaction rates in terms of their, see if I draw this right, like this is NO2. And then we got that for NO and like this for O2. As we proceed over time, this is molarity, the rate of reaction is variable, right? A change in this per change in time is the slope of the line, isn't it? A change in y divided by the change in x, which is what we did. Oh, I erased it. So the slope of the line, when you have a curve like that, you have an instantaneous slope. So at any point on here, the tangent to that point is the slope of the line at that point. So it's that way, and then as we get less and less of NO2, the slope of the line shallows out and the rate decreases. Okay. Now that's characteristic of this reaction. Some reactions behave differently. And that's a key point. This study of kinetics is extremely empirical. In other words, you can have a balanced equation and it tells you some things about the reaction, but the rate of the reaction has to be determined for the overall reaction. The rate has to be determined experimentally. You can't deduce it from the balanced equation. All right. So the next slide hammers that instantaneous rate home. So any place on these curves, a tangent to the curve at any point determines the rate at that point. So at any time t, the rate is going to be here, 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 with respect to any one of those components. Okay, so let's see, did I skip something important? No, okay. So we can express the rate of a reaction in terms of a law. And when we say rate law, we're saying the rate, and the rate can be in any units of measure. Usually it's molarity per concentration of molarity per second or per minute or per hour, depending on how fast the reaction goes. But we just leave rate as a generic. And then we say there is a constant value that we can multiply by, and they're sticking with that decomposition of nitrogen dioxide. So our term in here is going to be the concentration of nitrogen dioxide carried to a power. Okay, so we've got two variables here. Well, this isn't really a variable, it's a constant. And then this one is fixed for the reaction too. But these are both experimentally determined. And while this is the rate constant, N is the order. That's the order of the reactant in this case. Like I said, it has to be experimentally determined. This is what we would call a differential rate law in calculus terms. We're going to look at rate laws in terms of the integrated form that introduces a time variable in here, which is sometimes more useful. Well, we'll get to that eventually. Okay, in this expression of the kinetics of the reaction, this rate law, notice that the concentration of the products don't appear. And that's because we're studying this reaction under conditions where the reverse reaction doesn't contribute to the overall rate. That is, this is an expression of the initial conditions, rate law, at the very beginning. So that's when the rate, the slope of that line is the steepest. The slope is right here at the very beginning. And I'll say again, that N has to be determined experimentally. And we'll have a lot of fun doing that. You can't write it from the balanced equation. Yeah. Now, I will say this, when we get to the point where we're talking about mechanisms, where that overall reaction can be broken down into elementary steps. And it goes step 1, step 2, step 3 to get from here to the end of the products. Then we can use the coefficients and the elementary steps to deduce the rate law from those. So we'll get there. Okay, I mentioned differential versus integrated rate law. The differential rate law is the way we write it here. It shows how the rate of the reaction depends on the concentration only. The integrated rate law shows how the concentration of any of the species that you put in the rate law depend on time. So we introduce a time factor. And we're going to do that in just a minute. Yeah, that's restating. That summary restates the obvious. We're going to study reactions predominantly for initial rates. Although, actually, in the experiment that we're going to do next week, we're going to graph the whole thing, concentrations all the way through, and see what the determine the rate law from all the data that we collect. Oh, that's a good point. The second point, because the differential and integrated rate laws are for the same reaction and one is derived from the other, if you know the one, then you can derive the other, right? So sometimes it's more convenient to attack the rate law from the integrated side and then deduce the differential equation. Sometimes the differential equation is more useful. And then there's another factor that we're going to introduce. It's called half-life. How long does it take for half of that reactant to disappear? Right, and then we'll introduce that too. And sometimes the data that you have is better approached from that angle too. So actually we got three angles that we can deduce data for our, or deduce outcomes for our reactions. Once we know the rate law for an experiment or for a reaction, it becomes a little easier to infer individual steps, those elementary steps for the reaction. And that comes with experience and education. Okay. So with one term, this is the order of this reactant. If we have more terms in here, and we can have, if you've got two reactants or three reactants, you may want those additional terms in here. Then we'll have an order for each one, and they don't have to be the same. So once you find the order for each of your reactants, then you add them up. So if we had another value in here, M, N, M, maybe another one, or P, then we would just add them all up. And that would be the overall order for the reaction. All right, this method of initial rates is one where we start at time zero with a concentration of reactant. And we watch the reaction proceed at the very beginning. That's where we're interested, where we don't get any reverse reactions. Okay, I already did this slide. Overall reaction, the order, just add up the individual orders, and that's the overall order for the reaction. So just check, how do the exponents or orders in a rate law compare to the coefficients in a balanced equation? They don't. They're not related at all. The balanced equation is an expression of stoichiometry. It doesn't say anything about how fast it takes the reactants to get to the products. Okay, so we're going to take data sets and say something about the order of the reaction in terms of one of the reactants. Right? Got to keep it really simple at the beginning. And we're really only going to focus on three different orders, where n equals 0, or it equals 1, or it equals 2. So 0, first and second order equations. And we're going to characterize those. Those are the most common. But when you actually do the calculations and determine the order, which is what we're going to do with the experiment that we planned for next week, the order doesn't have to be a whole number. It can be a fractional number. We're going to, for simplicity's sake and for understanding at the beginning, we're going to concentrate on whole numbers 0, 1, 2. Okay. So I'm going to need room for this. So the key is, if we measure the rate of a reaction, and we find that the concentration of the reactant A doesn't matter. It's 0 order, all right? Anything to 0 is 1. So under those conditions, let's see, this is 0 order. Under those conditions, then the rate equals, right, whatever our reactant is, 0 to the 0 power. There's a rate constant. So that means the rate is equal to a constant. So that means that if A is the reactant and it disappears over time, what you'll see plotted is time versus the concentration of A, and this is the beginning concentration, A here, A 0, then it'll be a straight line decline. That's a zero order. And I had some documents that derive the integrated rate law. They use calculus, but I thought, you know, if you haven't had calculus, it won't make any sense. So I'll just give you the derived equation. You take this differential rate law and you introduce the time factor into it, then we get the integrated rate law. We find that at any time t, we can calculate the concentration of A if we know K, which it will be a minus because that's a negative slope, times T, plus the initial concentration of A. That will be our integrated rate law. Notice the way this is plotted. If you plot, this is X, this is Y. If you plot the concentration as is against time, you get the straight line. If it's zero order. Okay? And that's what it would look like. Now, introduce half-life. Right, this is another calculus thing. So the half-life, T1/2, for this zero order reaction, we need to know the initial concentration and divide it by 2 times the rate constant. That will be the half-life for this reaction. And in this case, the half-life depends on the initial concentration plus the K, on both of those factors. So what we do notice is as A decreases, the half-life decreases. Takes longer and longer and longer to use up half of what's left. All right, for the first order equation, you can probably guess what the rate law is going to be. It's going to have its constant. It's not the same constant as that one. And then its initial to the first order. Now, you don't have to write the 1 in there, but you can just to satisfy. And what we find is if we plot T against A, we find that it gives us a curve like that. Right? We don't like curves. We want straight lines when we get them. So how do we get a straight line out of that one? You get a straight line by plotting not the raw data A, but the natural log of A concentration against T. Then you get a straight line. Okay. So the expression here is the natural log of A is your Y value plotted against, I think this is also minus K. Yeah, it's K times K times T, and then the natural log of the initial concentration. So we're starting to build a picture here. If you have a data set and you plot the raw data, gives you a straight line, you know you have a zero order. If you get a curve, then take the natural log of your concentrations and plot it. If you get a straight line, you got a first order. And then there's T1/2 for this one, which is 0.0. I got to go another slide first. So this takes the raw data and converts it to natural log and then plots it on that graph paper. And if we calculate the T1/2, Notice that for a first order reaction, it does not depend on the concentration of A at all. So the concentration of A can be anything. The half-life is not going to change. As long as the K is the same, the half-life will be independent of the concentration of A. All right. Oh, they're gonna slip a little first order question on us. First order reaction, 35% complete at the end of 55 minutes. What's the value of K? All right. We're told it's first order, so we know it's going to be this expression plotted this way. 35% complete at the end of 55 minutes. So what does that mean? Well, let's see. Let's put our data up here. If we have a concentration of A, and then the natural log of A, and then time, and time is in minutes. Okay. It's 35% complete at the end of 55 minutes. So if we start at 0 time, then after 55 minutes, whatever we started with here, it's going to be 35% lower. So if we started with 1 here, then it's going to be 0.65, correct? 35% complete. That's what's left after 55 minutes. What's the value of K? Well, I'm not sure why I put that in there. Let's see. I took the integrated rate law and solved it for, oh, I know why I did this. Yeah. I ran the equation backwards and set it up so I could get a ratio of A to A0, what we started from. So this value is equal to the ratio of A to A0. If it's 35%, then we've got this much A left over relative to what we had. If this is 1, this would be 0.65. And the ratio would be the same no matter what. 0.65 is the ratio. So I needed an expression of ratio. So I took that equation and I worked backwards until I got the numerical ratio of A and A0, which is equal to E to the minus KT. Right. So now we know that we've got 65% is the ratio of A to A0. So at 55 minutes, we have, let's see. So the ratio is A to A0 is 0.65, and that's equal to E to the minus KT, minus K, and T is 55 minutes, correct? Let's see, there it is. Minus K is 55. So now that we have this expression right here, how do we get rid of that E? Take the natural log of both sides, right? So the natural log of this side, 0.65. The natural log of E is the exponent of the E, right? Because the base of natural log is E. So E to what power is equal to that? It's this value right here. So that's minus K 55. There we go. Remember your logs. Way back in the Stone Age. So then all we have to do is say, all right, K then is going to be this log K. That's minus K. So I'm gonna put the minus on that other side also. Natural log of 0.65 divided by 55, negative number. All right, so I just take the natural log of this divided by 55 and change the sign. And we come out to 7.8 times 10 to the minus 3. K equals 7.8 times 10 to the minus 3. Now, sometimes we can put units with it, sometimes the units don't matter. I mean, they matter, but they can be so complicated and be complex that we generally just leave them off. And be careful about working with your equations. Okay. Now for second order. That was a first order problem. Second order.
How many orders are there?
3, 0, 1, and 2. The only ones that we're going to study. So in this case, the differential rate law is still K times A to the second power. And if we plot time against A, then we get that curve. So we know we can't use that because we don't like curves, put it that way. So what we've discovered is for second order equations, the integrated rate law tells us when we plot T against the reciprocal of A, that will give us a straight line. So the integrated rate law here equals positive KT plus 1 over A 0. Okay, so just take the reciprocal. So here's what you do. And this is going to be a positive slope, right? That's positive. When you get data and the question is it 0 first or second order? Set it up in a spreadsheet if you can. Or you ask yourself the question, plot time against raw data, time against log, time against reciprocal, and see which one is the straight line. The one with the straight line tells you what order it is with respect to that reactant. And this is what a conversion looks like for this particular decomposition of ethane. No, that's butane, excuse me, C48. No, that's not even butane. What is that? C4. It could be butene or butane. I don't know. Anyway, when you plot the reciprocal, you get that straight line. Now, one thing you have to remember is if you're going to use that plot to interpret the data, you got to remember that that's not A, that's the reciprocal of A, and that's not A, that's the log of A. So if you go in and say, all right, what's the concentration of A at time blah? You go here and you go up here like that, and you read off a value. That value is not the concentration of A. It's the reciprocal of A. So you got to convert it if you want to say something about the concentration using the graph to interpret. And then there's a half-life for this one also. 1 over K equals 1 over K A0. Okay. So this one does depend on the concentration of A. Only it's the reciprocal concentration. So as A, if we increase A, we'll decrease the half-life. All right. So let's see what we got here. We're going to say take A to products A0 is 5 molar, and the first two half-lives are 25 and 50. All right. So let's make a table out of this one. See, is that still? I don't see myself. Show taskbar, setting, split setting. No, that's not what I want. That's not it either. I don't want that either. Okay. I just have to assume that I'm catching everything out here. I'll try not to get too close to the edge. All right, so if we've got concentration of A, and then we've got time. The first concentration of A0 is 5 molar at time 0. The first two half-lives are 25 and 50 minutes. So after 25 minutes, how much A do we have? 2.5, half-life. The second half-life takes this as A0, and it goes another 50 minutes. So that means the overall time now is 75 minutes. Because the half-life went from 25 to 75. This is 50 minutes for the next half-life. That means this is cut in half again, 1.25 molar. That builds our data table. So what's the rate law for this reaction? Calculate the K and then say how much A is left after 525 minutes. So I think I've got it animated. Yeah. Notice that the half-life changes with concentration. Right? The first half-life is 25 minutes, the second half-life is 50. So which one can it not be? It can't be this one because the half-life depends upon the concentration of A. The half-life changes with A. Here, it doesn't change. So we can throw first order out right now. So if the rate law were 0 order, then the half-life would be A0 over 2K. Right? Okay, I think it's going to be calculated here, so I don't have to write it. So we take that and we calculate the K value based upon the half-life. All right, so 25, we use 25 minutes and the initial concentration of 5, plug it into that half-life, and we get a K value of 0.1. If we do the same thing, now the new A0 is 2.5. And that one takes 50 minutes. So we plug those values in, and we get a K value of 0.025. Right? It cannot be 0 order because K is a constant. Right? The K changed. Right? So process of elimination, it's probably second order. All right, we're going to go ahead and calculate it just to prove it. All right, so if we plug those values in like we did before, we get the same value, 1 divided by 125 for both Ks. That nails it. So we have a second order equation for this data set. And that means the rate equals K times A to the second power. But that doesn't help us much for calculating how much is left after time. We need the integrated rate law for that one. All right, there's the K. So what does the integrated rate law look like? All right, it's going to be the reciprocal of A equals K times T over the reciprocal of A0. We know what K is. We know what time is. 525 minutes. And we want to know this value. So if we start with 5 and we go for 525 minutes, that gives us a time of 525 that we put in the T position. And then we plug the K in. And now we say A0 is 5. That's in the intercept position on the right. Now we have an equation with one unknown, and we solve for the A. And it turns out that with this data, we can determine that the final concentration will be 0.23 molar after 525 minutes. Okay? Oh, there it is in one fell swoop. Okay, this is just a reminder. How can you tell the difference between first and second order rate laws from their graphs? Oh, I guess I was supposed to say something. Just like I said before, you take the raw data, plot it, take the natural log, plot it, take the inverse, plot it. The straight line tells you which one you have. Okay. So what do you do if the reaction rate depends on the concentration of two reactants? Because we've only talked about one reactant changing into something else. Well, you do what we're going to do next week. If you've got two reactants, A plus B yields something, products. Then what you do to study one of them is you make the second one high concentration so that you can assume it does not change during the reaction. It is essentially constant. Then you can focus on this one. And once you figured out what the order of this one is, then you can go back and vary this concentration. And now that you've got this one nailed down, you can look at that one. So that's what we do next week. We're gonna bleach blue dye, blue food color. And we're gonna find the order of the reaction in terms of the dye with a very high concentration of bleach that essentially doesn't change. And then we're going to do another experiment where we let the bleach concentration change and the blue dye is held constant. And then we look at that one as a separate item. And I think the handout I gave you has some added information at the back describing, yeah, I mean, this is the latest version. Hopefully, we'll have time to talk about it today. Yeah, after we finish this. So that's what you do. Right? You increase the concentration of the second one so high that it doesn't change during the reaction. And how do you deal with the rate constant? Well, if the B doesn't change, it's essentially constant. And then there's another K, the K that you're interested in, you combine the two. K and B to its power is constant. So that gives you a pseudo rate constant that we put a little tick mark by it. And that's the first one that you determine. Yeah, that's right. A complete discussion is in the kinetics lab. But that's where we're headed. So we can't stop at the K prime. That's not the K we want. So once we find out what the order of A is, then we go back and do another experiment with a different concentration of bleach and determine what the rate is for that one. And then we combine those two equations and solve the K prime for the K. All right, so this table came out of my textbook and it just puts all this together in one place. That's the only reason for that slide. Okay, let's see. if A is 5 molar and K is 1 times 10 to the minus 2, assume the units are appropriate for each case. Calculate A after 30 seconds have passed, assuming the reaction is. Okay, so we're going to take this information and we're going to see how much A is left after the 0 first and second order. Right. We're going to change the conditions ourselves. So the 0 order has an integrated rate law that looks like that. And we plug in the values that were given for K, initial concentration, and time. And we find that after 30 seconds, if it's 0 order, you got 4.7 molar left. Right, so a lot of it's left. 0 order is a slow reaction. First order, if we do the same thing, we find that we only have 3.7 molar left. So first order is moving faster. And then if we do the second order, same thing, we only got 2 molar left after 30 seconds. So the order does have something to say about the speed of the reaction. All right. Now there's a method for handling equations with more than one factor that requires initial rates. This whole thing is a method of initial rates. And what we do is we choose the concentrations based on our experience of the components of the reactants in such a way that we have enough separate experiments and we determine the rate for each experiment. All right, so in this case, let me go to the next one. In this case, we have 4 separate experiments. The first one has 1 times 10 to the minus third molar, 1 times 10 to the minus third molar for the second component, and 1 molar for the third component. We get a rate. Then we go back and do the whole thing over again with different concentrations and determine another rate. Notice that we let the manganate ion vary in concentration. And the second and third components stay the same. We do that for a reason. Then we go down to the third one. Now we're going to hold the first one and the second one constant. No, the first one and the third one constant, let the second one vary. And the last one, we hold the first and the second one constant, and the third one changes. Okay, there's a reason for that. Right, now I'm going to show you why. So the question is, what's the rate law? So what we're after first, I guess I'm going to have to work it out myself. Okay. I think I'll do this one in detail.
Okay.
For the first exposure to initial rates, we'll do this one in detail. So what I need is to put that data set up here. Actually, I need to put the reaction that we're working with. So we've got 2 MnO4, 2 M. Let's see. Put it over here. 2 MnO4 minus, and then 224. Five plus 5 C2H2O4 plus 6 H plus. So this is an acidic solution. And then we have products. And they don't matter for our calculations. Mn2 plus, and then carbon dioxide. They only matter for the stoichiometry and the 8 waters. Okay, so for these, we run these 1, 2, 3, 4 experiments. I'm going to give them Roman numerals 2, 3, and 4. And we get data for each one. So we got 1 times 10 to the minus 3. And the rest of them are 2. And the next one, we have the first two, 1 times 10 to the minus 3. And the last two are 2s. Okay. And then for this one, we have 1, 1, 1, and 2. And then we have a rate out here. Rate. So the rate for the first experiment was 2 times 10 to the 4th minus 4, and 8 times 10 to the minus 4, and 1.6 times 10 to the minus 3, and then 1.6 times 10 to the minus 3. Okay. If you make this 10 to the minus 4, that'll be 16. So it's like 2, 8, 16, 16. All right, so what do we do? Well, we write the rate law first, so we know what we're looking for. So the rate law in this case would be a K value, concentration of MnO4 minus, and let's see, I'm going to use M here as an order for that one. And then we have C2H2O4, that will be N. And then we have hydrogen, would be P. I don't want to use an O because it can be mistaken for it could be mistaken for the order. Okay, so that's what we're looking for. We're going to find that one, that one, that one. Here's the way you do it. You take that rate law and you substitute values in, and you divide one experiment by the other. You usually pick the ones on the numerator is going to be the higher value. So we're going to put 2 over 1. These are the same, different. So the first one we're going to experiment 2 divided by experiment 1. And that's going to be K on top times the concentration of MnO4, 1 times 10 to the minus 3. And then 1 times 10 to the minus 3. And then hydrogen is 1. Okay. And then we're going to divide that one by this one. It's also K, right? The K is the same for always. This one's going to be 2 times 10 to the minus 3. And this one's going to be 1 times 10 to the minus 3 and 1. Okay. And then we need the rates. So the first rate is 8 times 10 to the minus 4 divided by 2 times 10 to the minus 4. Okay. So now, I left out this is M, this is N, this is P, this is M, this is N, this is P. Notice that these two terms cancel. These two terms cancel. These cancel. So we're left with, wait a minute. I guess that's okay. These 10 to the minus 3s cancel and you have 1/2, right? 1/2 equals 8 divided by 2. So that's 4. Only this one is M. Okay, so what power of M will give you 4? Something wrong with that. Did I write it up there correctly? 1, 2. No, I did it right. No, I didn't. I thought it looked weird. Put them on the wrong side.
Mhm.
This one, for that rate, this is 2. And for that rate, it's 1. Okay, so this is 2 to the M. All right, so 2 to what power equals 4 is 2. M equals 2. So now we know that this one is 2. Okay. Next thing we're going to do is look for the one where this is varied and these two are the same. So we're gonna have K again. We have different values here. Maybe. I'm just gonna erase them all anyway. Okay, so which experiments let this one vary and hold these two constant? Well, let's see. This one goes from here to here. That one's the same there, that one's the same there. So we can use 3 divided by 2. Okay? Now 3 is going to be 1.6 times 10 to the minus 3, and 2 is going to be 8 times 10 to the minus 4. And the values here are going to be 2 and 2. The value here is going to change. It's 2 here and 1 here. And this is going to be 1 and 1 again. All right, so these, I'm sorry?
I was just, go ahead, see what cancels.
Cancel, 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 cancel. So what we're left with is this one, 2 to the n is equal to 1. Okay, so this, if we make this one minus 4, that's 16. So 8 to 16 is 2. So n has to be equal to 1. Okay. Now we got this one equal to 1. All right. Next, we want to find out about the hydrogens. Okay. Which ones lets the hydrogen vary here? We go from 1 to 2 here. These are the same. These are the same. So we'll do 3 and 4, or 4 and 3. Okay. So these are going to be 2 times 10 to the minus 3, 2 times 10 to the minus 3. These are going to be the same. 2 times 10 to the minus 3. And these are going to be 2 and 1. This is going to be 1.6 times 10 to the minus 3, 1.6 times 10 to the minus 3. Okay. So these cancel, 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 cancel. We're left with 2 to the p equals 1. Right? 1.6 divided by 1.6 is 1. So p equals 0. 2 has to be 0 power to equal 1. Yeah. So this is 0 order. Now, this is information, but when we write the rate law, let's see. Oh, we're not finished. We have to find the K. Okay. So now we're going to find the K. So we just pick one of these. Doesn't matter which one. Like pick the first one. Question? Yeah. Okay. So the rate is 2 times 10 to the minus 4 is equal to K times this value, 1 times 10 to the minus 3 to the second power, and then 1 times 10 to the minus 3 to the first power, and then this is to the 0 power. So it's going to be 1 anyway. Doesn't matter what it is, but it's 1. Now we have an equation with one unknown. We just have to solve for that K. So we're going to say K is equal to this one, divided by that one, divided by that one, divided by that one. Right? Okay. So let's do that. 2 exponent minus 4. And then we got to square that one. 1 exponent minus 3 squared and divided. Okay, then I should have cubed them. 1 exponent 3 divide again, and that's 1, so it doesn't matter. So K, I get K equals to 2 times 10 to the 5th. All right, so if we substitute here 2 times 10 to the 5th, we have our rate law. Only we drop that term because it's 0. And let's see, does that agree with this one? 2 times 10 to the 5th. This one to the second power, that one to the first power. And if it's a 0 order, the term drops out. Because the rate doesn't depend upon concentration. Okay?
Once you learn how to set up, they're not hard to figure out.
No, this type of problem is fairly easy. I think the real problem is for the experimenter figuring out how to pick the numbers. That takes experience to get to put the right concentrations in there so you have a measurable rate in a reasonable amount of time. Okay, so that's the method of initial rates. Now one slide took forever.
Mhm.
All right. So now we're talking about mechanisms. When we say reaction mechanism, that's the individual steps that can be identified, in quotes, for a multi-step reaction. Usually, when we write an overall equation, it's a combination of at least 2, maybe more steps, initial steps, where if you have multiple reactions, maybe 2 of them react and produce some intermediate. And then that intermediate reacts with something else, and they work their way down until you get to all the products. Those elementary steps. Okay, here's an example. NO2 plus CO yields NO plus CO2. This has been determined to be a 2-step reaction. So the first one there, right here, see that? No, you don't see that. It's not showing up over there. The first step has NO2 reacting with another NO2 and producing NO3 plus, NO2 use NO3 and NO. That's the first step. Then we take that NO3. Notice NO3 is not part, it has no place in the overall reaction. It's an intermediate. So we take that NO3 now and react it with carbon monoxide. And the carbon monoxide regenerates an NO2 plus the carbon dioxide. One characteristic of these elementary steps is you have to be able to add them together and get the overall equation. So in this case, maybe I better write it up there. Step 1, let's see, NO2 plus carbon monoxide yields NO plus carbon dioxide. Step 1, we have NO2 reacting with NO2 to make NO3 plus NO. Then we take this one in step 2 and react it with CO. And that gives us NO2 plus CO2. All right. So notice when we add these together, we should get this equation. Right? We've got 2 NO2s here, but one of them is regenerated over here. NO2 on this side, NO2 on that side, they cancel. So that leaves us with 1 NO2. NO3 on this side cancels that NO3. So we actually have NO2, and we have CO, And then here we have NO, and there's CO2. So when you add the elementary steps together, you get the overall reaction. That's the first condition. And this is an intermediate. It's rare that researchers are able to identify intermediates. It's becoming more and more common, but it's difficult to identify intermediates because they happen so fast. So many of these elementary steps, the mechanisms, are proposed. And then you, by the process of elimination, you knock out the ones that make no sense, and it can't be, and you end up with one that makes more sense than the rest. It's like that Sherlock Holmes thing.
I know what you're talking about.
Yeah. So there are different types of elementary steps. So for this elementary step, we've got this reacting with that. This is called a bimolecular reaction. This is a bimolecular reaction because the two reactions, there are two of them. The unimolecular reaction would be one where you get a decomposition. You just have one and it produces something. The termolecular is very, very rare, where you have three interacting in an elementary step. The reason it's rare is it's very difficult to get three together in just the right orientation, just the right energy to react. We only use termoleculars when nothing else works. And when we talk about the orders, the unimolecular is considered a first order, bimolecular is second order, termolecular is third order. Now, the rate determining step depends on which one's the slowest. That's the one, that's the bottleneck. So the whole rate of the entire reaction is determined by which one of these is the slowest. I mean, we weren't told for this one, but it's still true. Sure. So here's the statement, that note statement. The overall rate law can't be derived from the balanced chemical equation of like this one. But we can derive an overall rate law if we know the elementary steps. So that's one of the ways we determine whether this mechanism is valid, right? We use it to derive the rate law and compare it to the experimentally determined one and see if they jive. If they do, then that's evidence that your mechanism is on the right track. All right. I've already covered this requirement. The sum of the elementary steps have to add up to the overall balanced equation. And the mechanisms must agree with the experimentally determined rate law. In other words, when you derive the rate law from the elementary steps, it has to agree with the experimentally determined one. Those two conditions are inviolable. All right. So for the decomposition of N2O5, we have the overall reaction there. 2 N2O5s yields 4 NO2s and oxygen. And the mechanism is proposed. N2O5 is in a fast equilibrium with NO2 and NO3. So that's what that double barbed arrow means. Plus, it tells us that it's a fast reaction. So it's often referred to as a fast equilibrium. What that typically means is as soon as N2O5 produces NO2 and NO3, they go back the other direction just as fast. So they're like this. The rate determining step is the second step, where you get NO2 and NO3 together to produce NO, O2, and NO2. And then you take NO3 and NO and produce 2 NO2s. If you add all those together, you should end up with the balanced equation. But in order to add them together, sometimes you have to manipulate them. Right? In this case, we multiply 2 times the whole equation of step 1. And that allows us to cancel all the NO3s, the NO2s, and the NOs. And if we do that, that leaves us with 2 N2O5s. 2 NO2s plus 2 NO2s is 4 NO2s plus the oxygen. So that allows us to add those together and equal the overall reaction. All right, let me see. Yeah, okay. So if we have this mechanism proposed, we got a fast equilibrium, A plus B equals D, and then slow is D plus B, you'll see that's the rate determining step. First of all, does the mechanism meet the first condition? Can you add those up and get A plus 2B, you'll see? And the answer is yes. The D's cancel, and you get 2 B's and a C and an A. All right, so that's the first condition. The second condition is, the second step is we apply a rate constant to each one of the steps. For the fast equilibrium, you've got a rate constant going to the right and a rate constant going to the left. And for the slow one, you've only got one going to the right. So we got K1, K minus 1, and K2. Those are important because we're going to use those values. So since the slow step is the rate determining step, we're going to write the equation for the slow step first. And if we do, there's rate equals K2, right? K2 is the slow step constant, and D times B. Remember, the elementary steps, we can use their equation to generate the rate law. This is the rate law for the slow step. Notice, though, that we've got a D in there, and there's no D. That intermediate is not in the overall equation. So we got to do something to get rid of that D. So what we do is go back up to the fast equilibrium and write, D is not a reactant. That's true. What we do is go back to the fast equilibrium and we say, all right, if they're the fast equilibrium, that means the forward rate is equal to the reverse rate. So if we write the rate equation for the forward reaction and it equals the rate for the reverse, we can say that K1 is the rate for the forward reaction times A times B, and that's equal to K minus 1 times D. So we set that up and solve for D, and then we take that and substitute it in for D in the slow equation. So that's what we've done there. So we've substituted the equivalent of D in that position, and now we can combine terms. And what we find out is that if K2 is constant, K1 is constant, and K minus 1 is constant, all those things together equals the constant. So our rate equation is K times A times B squared. So the overall should be A to the first power and B to the second power with that mechanism. Okay. Now, I sort of alluded to the collision model a minute ago when I was talking about the termolecular. The collision model simply says first that in order for a reaction to occur, molecules must collide. They got to bang into each other in order to break bonds and form new ones. So that's why the termolecular is so rare. It's difficult to get three molecules or three atoms to hit each other at just the right angle, just the right orientation, and just the right energy to produce the desired reaction. So the main factors we're interested in are activation energy. And activation energy is, let's see, have I drawn this before? All right, this is the progress of the reaction. And say this is the potential energy of all the components. So if we start here, let's see, let's start up here. These are the reactance energies all together, all the reactance energies. When they collide, or when they get together, whatever mechanism we choose, they need energy. And they go to the top. And this is the activation energy, difference between here and here. Right? This is activation energy, difference between there and there. That amount of energy is required. And if they get to that point and just a hair past, they go over the other side. And now we got products at that energy level. Have I shown you this one before? Okay. So if the potential energy of the reactants is up here and the potential energy of the products is here, that means the difference between the two right here is delta H. That's the enthalpy of the reaction. Okay. This is, sometimes it's referred to as activated complex. Right, once it reaches this point, and if it's at the activated complex, it only needs just a slight amount of extra energy to get it over the hill. So if it's up here, it can go down the other side, or it can go back. So we're going to talk about next chapter, my chapter 13. We're going to talk about this part here and this part here. These two sides together are equilibrium. This part in here is kinetics. Activation energy references kinetics. And so the activation of the energy is innate to the reaction. And then external to the reaction is the temperature. That's the environmental factor. If we increase the temperature, we're increasing the energy, the potential energy of the reactants so that they can make it to the top and reach the activation energy. And then the last factor is molecular orientation, right? If you've got enough energy and say you have a bimolecular and these things are coming together and they smack each other with sufficient energy, activation energy to get to the top, only they're not oriented correctly, right? The reaction sites have to be on this side. Then the reaction won't happen. So that's another probability problem.
It's a
Okay.
delta H.
Enthalpy. Yeah. We did calorimetry last semester, didn't we? Yeah. That was just kind of touching on it. We're going to get into more depth this semester. Okay, this is the energy that must be overcome to produce the reaction. And upcoming, here we go. So here's an example. There's the transition state. I call it the activated complex. It's also called the transition state. And it's a quasi-stable state. In other words, it could go either way. It could go down to products or it could go back to reactants. So the collisions have to involve the right amount of energy to produce the reaction. That's activation energy. They have to be oriented correctly so that the bonds that need to be broken and reformed are in the correct position for those atoms to establish their new bonds. So here's Svante Arrhenius came up with this one. This is his differential equation that relates the activation energy to the temperature and to other factors, right? A is experimentally determined and K is the, I think K is the rate constant. Yeah, K is the rate constant. So you can calculate the rate constant if you know those factors, but they're not very useful. That equation isn't useful as a practical matter. What we need is an integrated rate. And that's what this one is. This is the linear form of the Arrhenius equation. And what it says is, if you have two or more experiments at different temperatures, and usually you do more, different temperatures, and you measure the rate constant, then if you plot on the y-axis the natural log of the rate constants for the different temperatures, and then the temperatures, the inverse of the temperature on the x-axis, you get a straight line. And the slope of the line is a negative activation energy divided by the gas constant. Okay? So that's what's on the next one. So if you're given that data, if you're given the equation for that line, then all you have to do is go back to what it means. The slope is going to be equal to that, right? If you have the slope, then you can calculate the activation energy, because the gas constant is 8.3145. And it's a constant. And you can also derive the K. Well, you are going to have the Ks. So what we're after is the activation energy for that reaction. Okay, let's see. Oh, all right. I've got this one worked out too. I've always heard this rule of thumb. And if you've had a biology class, you've probably heard it too. If the temperature in Celsius is increased by 10 degrees, the reaction rate will double. And that's just a rule of thumb. It varies all over the place. Or if you decrease the temperature by 10 degrees, you cut the reaction rate in half. So if we go Celsius, let's just keep it simple. Say it's 20 degrees, 68 Fahrenheit. And we decrease the temperature to 10, right? It's getting chilly. Reaction rate is going to be slower. So food will spoil, take longer to spoil. And then we go 10 more degrees down to 0, right, freezing, then the reaction rate cuts in half again. So what we do is we typically store our foods, if we're going to store them for a long time, we'll freeze them at minus 20 degrees Celsius. So that's gone 40 degrees. Right? So 40 is how many steps? It's 4 steps. Right? So we cut the reaction rate by 2 to the 4th power. Okay. Or you can do the blast freezer thing that I did once a month and inventory the product. It's down to minus 40. So we've gone another 2. So that we cut the reaction rate down there 2 to the 6th. Okay. What I wanted to know when I created this slide was, what is the actual activation energy required for a reaction to fit this rule of thumb? So I had to pick degrees. So I said, okay, let's say between 25 and 35 degrees. That's a 10-degree move. Then I went to the Arrhenius equation. So on the left-hand side, I've got I'm going to use the differential Arrhenius equation for this one. And the reason being, when you ratio them, then those factors that you would normally have to determine just cancel out. So they're not a problem. Right? So, but we have to use the K temperature. So the K temperature for 25 degrees is 298, and the K for 35 is 308. And what we notice is that K1 if the reaction rate is going to be cut in half, then that's the second rate at 35 degrees, it would be double of the rate. So the K2 is equal to 2 times the K1 in order to double the rate. So now we ratio K2 to K1, which is actually 2K1 over K1. And then we ratio their equivalents in the Arrhenius equation. And now what I've done is just reduce everything. The A's cancel. And then E to a power divided by E to another power is the same as E to the numerator minus the denominator. And that's where this one, that next to the last one came from. And then we combine terms and go to the next. So what we've got here is 2 equals E to that monstrosity. And in order to go to this next one, I took the log, excuse me. Yeah, I took the log of both sides. All right, so the log of 2 and the log of E to the power is the power. So that's where the next one comes from. So there's the power that we had, and here's log of 2, and I just moved the R over from underneath E to the A. And now that I've got, I'm trying to get E to the A on one side of the equation and solve for the rest of them. Now that I've got an equation and I have values for T1, T2, and R, I plug those values in, and the activation energy that would satisfy that rule of thumb is 52.9 kilojoules. Interesting. I don't know if it makes a big bit of difference though. It only works between 35 and 25. Okay, now what's a catalyst? I'm sorry?
Let's speed up a reaction.
Yes. Catalyst causes the reaction to proceed more quickly, increases the rate. But it's not consumed. It participates in the reaction, yes, but it goes in the front end and comes out the back end. Unchanged. What it actually does is it provides a different pathway for the reaction. So when you put a catalyst in there, you're actually changing the mechanism, the elementary steps for that reaction that have a lower activation energy. So that's what this slide is showing you. Right? The activation energy would normally be that top purple line. But with a catalyst, it takes less energy because you have a new pathway. And the catalyzed pathway is in the blue line, shows you a lower energy required. Now, what it does not do is it doesn't change the enthalpy of the reaction. It's exactly the same, even though it occurs faster. Aluminum, it depends on the reaction. It could be. Yeah. Oh, yeah. Yeah, that's right. Yeah. It's an organic catalyst. The only other one that I know is of great significance is the Haber-Bosch process. Fritz Haber needed a catalyst to speed up his reaction, where he took nitrogen plus hydrogen and made ammonia. He speeded up the reaction with iron. He took iron very finely divided, like this pack on my back here. At those heating pads, they're nothing but powdered iron. And the iron reacts with oxygen and gives off heat. So you slide them in this pack and position it where your sore muscle is. Yeah, and I've got one right back here. It's not bothering me too much right now. But for Haber's purpose, the iron was a catalyst for that reaction. And it's dirt cheap. I mean, the availability of finely divided iron is nothing. So he had all the nitrogen from the air. He had the iron catalyst. He had hydrogen. I think they probably got hydrogen from methane. And they made ammonia and then gunpowder for the Germans during World War I. Okay. So what is it that speeds up the reaction? Let's look at it in a different form. In any assemblage of reactants, you have a distribution of energy of the reactants. So this is one example of a distribution. The energy of the reactants and the number of collisions with a given amount of energy. So that's what's on the y-axis, and the energy is on the x-axis. So as you increase the amount of energy, you reach a point in the middle where that's most of the reactants are at that energy level. But it's not enough to promote the reaction. You need to get beyond it into that blue area for the left one. That will give you enough energy to meet or exceed the activation energy. That's an uncatalyzed reaction. When you introduce a catalyst, now you've reduced the activation energy, so more of the reactants have sufficient energy. So you just move that blue line over and you get more. So more reactants reacting means faster reaction. Now the different types of catalysts, right? There are heterogeneous catalysts, which means that the catalyst is in a different phase than the reactants. So the Haber process is a prime example. Iron is a solid, finely divided powdered iron or granular iron is a solid, and the reactants are all gases. So there you have a heterogeneous catalyst. Very often what happens is if the reactants are gaseous and the catalyst is solid, they adsorb to the surface of the catalyst. That's enough we say about that. You can also have, let's see, more about heterogeneous catalysts. So what happens with the reactants and the catalyst are, first the reactants are adsorbed to the surface, and their energy now is sufficient to make them active. And they typically, when they're on the surface, they'll migrate toward each other. And now if they have more energy, they'll form the activated complex on the surface, and they react on the surface, and then they're released as products. And here's a perfect example of a solid catalyst. You have platinum and palladium on this ceramic matrix, and exhaust from your engine runs through it and promotes the reaction that generates innocuous products. I don't know if I told you before, but when catalytic converters first came out, what they had was in the catalytic converter, they just had little ceramic beads, and they were coated with the platinum and palladium. So shade tree mechanics quickly figured out all you needed was a big screwdriver, pop it in there, drain out all the stuff, and then braze over the surface, and you got an engine that runs good again. So they finally, the manufacturers finally figured that one out, and they got rid of the beads and replaced it with a honeycomb that you can't get out without taking the catalytic converter apart. Homogeneous catalysts. Those are the ones where the reactants and the catalyst are in the same phase. And so in the next slide, I got a video, and we're going to take hydrogen peroxide and decompose it with a solution of potassium iodide. So those are both in the same phase. Enzymes in your body are catalysts. They're special, very special types of catalysts. They catalyze most of the reactions in the body, or in a cell, are catalyzed for two reasons. First of all, under natural conditions, they would proceed too slow. They wouldn't support life. But the other reason is that you want control. And enzymes are very special catalysts that exercise control. And for most enzymes, they only catalyze a reaction in one direction. So if you have reactants in your cells producing products, then the enzyme on this side will make it go that way, but it won't go the other direction. If you want to go the other direction, right, you need a different catalyst. Now, there are some exceptions, and they're rather annoying exceptions too. And the other thing is enzymes are infinitely more efficient at their job than inorganic catalysts. Inorganic catalysts are just like there, and they say, all right, come on in, grab you here, grab you here. The enzymes are very specific, and they catalyze a reaction at much faster rates. All right, we don't have time to go into the theory behind that, but just take my word for it. Okay, let's watch.
Try yours. So that's the technique. Just dump it right in and see what happens.
Oh wow. Okay.
Okay. So
Whoa.
we're releasing
Okay.
lots and lots of oxygen gas. Okay. So why don't you go ahead and do yours now? Yours is a little bit different container. It's got, just dump it in really quick.
Okay.
Perfect. Yours is like more. And you just generate tons and tons of oxygen. It's being trapped by the soap, okay? It's like a supersized version of what kind of happens when you pour it on your body.
Sure.
Where that catalase enzyme breaks it down.
But again, we're not actually cleaning anything,
Well,
if you will.
Technically, the hydrogen peroxide, when it generates this oxygen, can kind of dislodge big hunks of stuff. This is like more of
So what they've done is they've taken 30% hydrogen peroxide, which is 10 times as concentrated as your medicine cabinet, and introduced a catalyst, the iodide ion. In addition to that, you've got a little soap in there that'll make it foamy, and then you've got food coloring in there, give it color. And
Is that what we're doing next week?
you want to do that one next week? Mm-hmm. I had a student in this class, I think it was. It's been several years now, but he and his girlfriend were expecting, and they did an ultrasound and found so they did a gender reveal by using this process.
That's cool.
So they put the food coloring in there for, blue for boy, red for girl. Only they got it wrong the first time. They went back for another ultrasound and found, wrong gender. So they went and had another gender reveal with the right color.
That's cute.
Okay. So that was the decomposition of hydrogen peroxide. Now, hydrogen peroxide will undergo this decomposition naturally at a certain rate. So that's what the expiration date on the bottle of hydrogen peroxide in your cabinet is all about. It loses its effectiveness. So it produces water and oxygen. And that's not balanced, but those are the products. And all the iodide does is speed this up. And the mechanism, the 4-step mechanism is right there on that page. So it's fairly complex, but it happens. Now it says the first step is the slow step. That's a relative term. It's slower than the other steps. It's the rate determining step, but it's much, much faster than the natural decomposition, the uncatalyzed decomposition. Other types of catalysts. Ozone has gotten a pretty bad rap. We produce ozone by various processes, internal combustion engines, electronics. I remember laser printers when they first came out were notorious for producing ozone. They were making people sick. So their quick fix was they take activated carbon bags and put them inside the next to where the ozone is generated, and it would absorb the ozone. until they could develop the technology where it wouldn't produce so much ozone. Now, ozone is a very effective disinfectant, and some large municipalities use ozone treatment of wastewater, sewage water, to destroy the organics and the bacteria and all the pathogens before they dump it back in the river. At least Atlanta did that. And I lived just down the street from a water processing plant in Atlanta, and they needed to deliver a lot of water to a certain section of the town. So they went right up this 4-lane highway and dug down about 20 feet, and they put in a pipe that I could stand up in to deliver water to a section of the town.
Oh, Lord.
But that's understandable. At that time, Atlanta had, let's see, Metro Atlanta was like 1.5 million people. Now it's probably about 4 million. Anyway,
4 million in Atlanta?
in the area. Yeah, I think there are 7 counties in the metro area. Yeah, it swallows up a lot of
Would you live
territory.
there now?
Huh?
Would you ever live there now?
No. I'd live with where my sister is. She's about 20 miles to the east. Yeah. In fact, one of my sisters, she's since moved out of there. She used to live in a place called Conyers. You know, I have their names on the tip of my tongue. The Fanning sisters, Dakota and Elle Fanning. They're from Conyers. Big deal, huh? Okay, so ozone can act as a catalyst in the upper atmosphere. And it destroys nitrogen oxide, produces nitrogen dioxide. And in the process, no, excuse me, ozone is the good part of the atmosphere because ozone is an extremely efficient absorber of ultraviolet radiation and protects the lower parts of the atmosphere from living things from exposure. So we want ozone in the upper atmosphere. We just don't want it down here where we can breathe it. And the nitrogen oxides, in other words, I don't know if they still do it, but Georgia, for a short time anyway, did away with automobile inspections for safety inspections like lights and brakes and stuff, but they kept the pollution inspections. So they had these stations set up and they'd stick this wand up your tailpipe and it would measure pollutants coming out of your engine. And if they exceeded a certain amount, you wouldn't get your sticker. You had to go get it fixed. But they would measure nitrogen oxides. It's a mixture of different ratio of oxygens to nitrogens. And when these things drift up into the upper atmosphere, they catalyze the decomposition of ozone. That's what this is. This NO is a catalyst. And notice it goes in one end and it comes out the other. And the overall reaction is simply O plus O3 yields 2O2. Okay, so what is O? O is a free radical. Free radical is any element or compound that has an unpaired electron, one or more. And if we look at oxygens, just the Lewis dot structure, right? Oxygen's got what? 6, right? 6 valence electrons. 1, 2, 3, 4, 5, 6. It's got 2 unpaired electrons. Right? So the single oxygen atom is a whatever I just said. I hate it when that happens. Makes me feel like Joe Biden. Yeah, there's a report that just came out, and
Poor guy. I want us to start with the bad one.
Yeah, as a person, I feel bad for him.
Me too, I don't.
I just want him to retire.
Me too, right, get out of there, but I feel bad.
Yeah,
He's like a laughing stock of the whole world.
yeah, and I don't think he even knows it.
No, and he's so old, like, he's just in La La Land, I don't even think he's like,
Have you ever seen any television shows, usually news programs, where Mark Stein is on? You know Mark Stein? He's from Canada, but he lives in
yes.
New Hampshire. He's a riot.
Yeah.
But he did this one bit on Tucker Carlson's show one
I
time,
love to.
and I've got it stored somewhere. And he goes into this rant about he speaks as if he's Joe Biden.
I know what you're talking about.
Oh, it had Tucker drooling on himself. It was a riot. Anyway, freons. Okay, freons have been identified as catalysts in the upper atmosphere, and they are responsible for decomposition of ozone also. So they form catalysts. They actually decompose in such a way that they produce this free radical chlorine atom. Right, so it has one unpaired electron, and it's nasty when it comes to ozone. So that's why at least the simpler freons, like the freon 12, were banned. And later on, some of the other freon substitutes were banned also. We're trying to find a freon that would work in refrigeration systems, but would not damage the ozone. Okay, that's the end.